Good morning, everyone. So, today we are going to discuss the last section of this chapter, which is minimum cost spanning tree. Till now, whatever we have studied, we have always considered a graph to be unweighted. So, if we need to introduce a weighted graph, then we have to associate a weight to each of the edges. And then the weight of the graph is sum of the weights of all the edges. So this is how we can introduce or we can have the weighted graph. Now once we have a weighted graph, then a spanning tree with minimum weight is called a minimum cost spanning tree or a minimum weight spanning tree. It means you need to pick a spanning tree whose sum of the edges, whose if you consider the weights of the sum of the edges, it gives you the minimum weight. Let us consider an example. So this is a weighted graph K4. You can see that to each edge we have associated a weight. So this weight is 1, this weight is 2. Now it could have 16 spanning trees. Some of them are as follows, but we can draw all of them. And out of 16, there are only 2 which are having the minimum cost or minimum weight as 6. So if we have to find the minimum weight spanning tree, then one of the option is that we enumerate all possible spanning trees and pick the one with the minimum weight. But computationally it is very expensive. So the better choice is to devise an algorithm which if we use gives us the minimum weight spanning tree. So we are going to discuss 2 algorithms giving the minimum weight spanning trees. This is another example where you can see the minimum weight spanning tree has been marked by bold edges. So let us consider the following graph, and for the following graph please do try to compute the minimum weight. And once you compute the minimum weight spanning tree, then think to devise an algorithm that always gives you minimum weight spanning tree. So if you try by yourself, then the minimum weight spanning tree comes out to be a spanning tree with weight 8. And there could be many ways for having this spanning tree, but what we are going to discuss is an algorithm. So to start an algorithm, we always start with an edge with the minimum weight. So let us say this is the minimum weight edge. Now I pick an edge again from the remaining edges having a minimum weight such that it should not form a cycle. So there are 3 choices, either this one, either this one, either this one. Any one of them can be picked. So I picked XY. Again, I have this structure. I picked this one and this one. So again, I pick one more edge having the minimum weight. There are 2 choices. I pick any one of them. Now I cannot pick U to W because it forms a cycle. So instead of that, I move to the other minimum weight edge, which is 3. So I pick this one. And now you can see that all the vertices have been covered, or you can say that the order of the graph was 5. So I was looking for only 4 edges. So these 4 edges have been identified, and that gives me the required minimum weight spanning trees whose weight is 8. So this algorithm is the Kruskal's algorithm, which keep picking the minimum weight edges, and we have to pick n minus 1 edges if the order of the graph is n, such that at any stage it does not form a cycle. And by doing so, in the end we will have a minimum weight spanning tree. So this is the Kruskal's algorithm. You first choose an edge with the minimum weight and then choose any edge with minimum weight from those not yet selected. The graph at this stage, the subgraph at this stage may be connected, may be disconnected, doesn't matter. But only thing is that you should not select an edge that creates a cycle in the subgraph. Now it's very interesting to provide a justification that why Kruskal's algorithm always produce the minimum weight spanning tree. Sometimes it's easy to develop an algorithm, but it is far more difficult to provide its correctness. So we will discuss the correctness. Before that, let's do some exercises. So for this graph, use the Kruskal's algorithm to obtain a minimum weight spanning tree. Please do try it by yourself. I can quickly show you the answer. So this is the minimum weight. I picked this one. Then the next, there are two choices, and since if there are more than one choices, it guarantees that the solution may not be unique. So two choices are there. I picked this one. Again the next choice is 2, so I picked this one because it is not forming the cycle. After that the next choice is 4, so 1 2 2 4. Then next choice is 4. After 4 the minimum weight is 6, but I cannot pick this one because it is forming a cycle, so I have to pick 7. So I can pick this one because it is not forming a cycle, so I picked this one. Then after 7 the last choice is, because E is not yet covered, and therefore I pick 9, and that gives me the required minimum weight spanning tree whose cost is 37. Now think of any other algorithm other than Kruskal's algorithm for computing the minimum weight spanning tree. Very interesting exercise. So if you give a thought, then in Kruskal's algorithm, one quick observation is that it is not taking care of connectivity. Initially or until the last edge to be added, the graph may be disconnected. But if you add an extra condition that you always try to maintain the connectivity, which means that instead of looking for a forest as a subgraph, if you look for a tree to be a subgraph, then that algorithm would be different from Kruskal's algorithm, and we call it Prim's algorithm. Let's see how it works. So Prim's algorithm starts with any vertex whichever you want. Once you start with U, you look for all the edges incidenting to U and pick the edge with the minimum weight. So this is the edge with the minimum weight. Now this choice is not allowed for the minimum weight because it gives you a forest, but we are looking for a tree. So there are only two choices. In Kruskal's algorithm there were three choices. In Prim's algorithm there are only two choices. You make a choice and reach here. After making this, this is not allowed. This again is not allowed because it forms a forest. So next choice is we pick this edge with weight 3. Now I can pick the edge with weight 2, and you can see that all subgraphs are trees, and in the end I will have a minimum weight spanning tree. So in Kruskal's algorithm, of course, there are more choices, but in Prim's algorithm, we can start with any of the vertex because we know that all the vertices need to be covered. So you can read the Prim's algorithm by yourself and then try this exercise. So find a minimum weight spanning tree using Prim's algorithm, which must start at vertex A. So when it starts with vertex A, this is the minimum weight edge which is incidenting at A. Now among all the possible edges having the minimum weight, the choices are 10, 8, 9, 8. So I pick the one with the 8. So I pick the one with the 8. Again, the minimum weight choices are 2. This is the minimum weight, so I reach here. One is not allowed because it forms a forest and I am looking for a tree. Now once I reach C, then I can choose 1. Once I reach 1, again I can choose 2. And now it's only E which is remaining. So the minimum weight is 5, and that gives me the minimum weight spanning tree having the minimum cost 22. So it can be easily observed that Prim's and Kruskal's algorithm may not generate the same minimum cost spanning tree. For this graph, Kruskal's algorithm is giving me the following minimum cost spanning tree. But Prim's algorithm, if it starts with ABD, it is giving the same spanning tree. But if it starts with C, try it by yourself, then you will find that it gives me a different minimum cost spanning tree. Now let's discuss the correctness of the Kruskal's algorithm. It's not an easy exercise, even it is hard to follow, but it's very important to discuss it so that we can understand that whenever we think of developing an algorithm, we always have to think of its correctness. Two things are always associated with an algorithm. One is complexity, and there is always a research which try to improve the complexity of the algorithms, but at the same time correctness is very important. So we say that Kruskal's algorithm always computes a minimum spanning tree. Why? So let assume that Kruskal's algorithm computes the spanning tree y, which is not minimum. So we are starting with a contradiction. So let y1 be a minimum weight spanning tree. I am representing it as M.Sc. So there could be many minimum weight spanning trees. Y1 is one of them, having most edges in common with y. Let E be the first edge to be added to y, which is not in y1. Recall that how the Kruskal's algorithm works. It always picks the minimum weight edge so that it is not forming a cycle. So if there is a cycle, then within the cycle, if cycle has 4 edges, it always picks the edge with the minimum weight. So now y1 union E or y1 plus E forms a cycle. Something like this. So there was a graph and you add an edge E. So y1 is a tree, and when you add an add, it forms a cycle. Now let f be another edge that belongs to y1, but f does not belongs to y. So somewhere here, and it belongs to the same cycle C. So this is the cycle C, f is somewhere here. If you consider the another tree y2, which is y1 plus E minus f, so what you do? In y1 you add E and deleted f. This is again a spanning tree. We are not claiming it's minimum or not, but it's a spanning tree. And since y1 is a minimum weight spanning tree, therefore the weight of y2 should be greater than weight of y1, which means that weight of E should be greater than weight of f. At the same time, observe here is that E is the edge, so there is a cycle in this cycle, in the original graph there is a cycle. So in this cycle there is an edge E, there is an edge F. And now when the Kruskal's algorithm works, what it does, it picks the minimum weight edge. It means the weight of edge E must be less than equal to weight of edge F, because E is the edge which is added to Y using Kruskal's algorithm. So there is a cycle. In the cycle, Kruskal's algorithm always picks an edge with the minimum weight so that it does not form a cycle. So it means that W of E must be less than equal to W of F. From 1 and 2, I can get W of E is equal to W of F, which means that weight of Y2 should be equal to weight of Y1, which means Y2 is a minimum weight spanning tree, but at the same time, how we obtain Y2? We add an edge to it which is from Y1 and deleted an edge which is from Y and deleted an edge which is from Y1. So even if you see Y2 as Y1 plus E, then Y2 has more edges in common with Y. So Y2 is a minimum spanning tree which has more edges in common with Y. But we have assumed that Y1 is a minimum spanning tree having most edges in common with Y, which is a contradiction. And therefore, I can say that we started with the contradiction, we end up with the contradiction, and this concludes that Kruskal's algorithm computes a minimum spanning tree. So proof can be read later in detail, but let's move to the next question. So consider a set of 5 towns. The cost of construction of road between towns I and J is AIJ. Find the minimum cost road network connecting the towns with each other. So first try to understand that what has been given. So we have given an adjacency matrix here of the graph K5. We can consider the graph K5 where weights are given and we can find a minimum weight spanning tree. But at the same time, the minimum weight spanning tree, the order is 5. I just need to pick 4 edges with the minimum weight such that they are not forming a cycle. So for example, from the first row I can say 3 is there. So I start with V1 and I added it to V2 and the weight is 3. From the second row again I pick 3. So V2 is adjacent to V3 because 3 is the minimum weight until now. Now the next minimum weight is either 5 or 7. So 5 is V31. So if I add V31, it forms a cycle. So I cannot use 5. It means I have to go to 7. So 7 means that V45. So V45 is there, which gives me 7. Still I need one more edge and the minimum weight is 8, which is V25. So I add V25, which gives me, and that gives me a required minimum weight spanning tree, which is what I am looking in this question. The next question is that prove that if a weighted graph has all weights distinct, then it has a unique minimum spanning tree. So it can be directly followed from the Kruskal's or Prim's algorithm because all weights are distinct. So Kruskal's algorithm picks an edge with the minimum weight and there are no two choices at any stage, and therefore in the end we will get the minimum, we will get a unique minimum weight spanning tree. But at the same time, if we do not use Kruskal's or Prim's algorithm, then we have to prove it theoretically. So we prove by contradiction, which says that let T and T star be the two minimum weight spanning trees. Yes. Now they have the edges. Among their edges, pick the edge with the minimum weight E, such that E belongs to T but E does not belongs to T star. Yes. Then T star plus E forms a cycle. And if I consider T star plus E minus F, then E is the edge with the minimum weight. And therefore, the weight of T star plus E minus F should be less than equal to weight of T star. But we have assumed that T star is a minimum weight spanning tree. So this is a contradiction. And therefore, we cannot have two minimum weight spanning trees when all the weights are distinct. So this is an exercise which you can try by yourself. So that's all from this chapter. In the next class, we'll begin a new chapter. Thank you.